All right, a variation on the vertical plate problem is what happens when you have an inclined plate. So I started this example in the context of mass conservation, but let's continue it. So imagine that we have a horizontal jet with speed v1 and thickness h1 that splits into two different flows once it strikes a plate. So basically some portion of it shoots up the incline with speed v2 h2, and some portion goes down the incline with speed v3 h3. So the way I'm drawing it, my intention is that this is supposed to be a two-dimensional flow, meaning that the flow goes infinitely into the page. So this is a sort of a planar jet being shot at the surface and then splitting into two, so that I don't have to worry about solving this kind of thing in a three-dimensional radial coordinate kind of situation. All right, so previously I had asked, so what I'd like to do is find, so given V1 and H1, find H1, H2, V2, V3, and I'm going to add a little bit to that now, which is also to find the reaction force that acts at the plate. So this would be the force per unit depth into the page. In principle, you could also look for the transverse force into the page that acts onto the plate. Oops, that's supposed to be a prime for per unit depth. But in fact, because I'm going to say that this is a frictionless flow, so let me finish writing this out. So if this is a frictionless 2D flow, and in fact I assume that it's a steady flow, so if the jet has been impinging for a long time, this will come to a steady state, then in fact there is no way for force to be transmitted in the transverse direction to the plate, because the way that a fluid does that physically is using shear stress. So for a frictionless flow, there is no way to transmit a transverse force to a plate. So just by inspection, the transverse force, just as a physical principle, has to be zero. Let me define this angle here as theta, and that means that this angle here is also theta. So that'll be necessary. Okay, so in fact, I don't need to look for that. That's zero. Okay, so just as a reminder, we solved part of this already. So we employed mass conservation to find that, or Bernoulli's equation. So we applied Bernoulli's equation first, actually. So Bernoulli's equation along a streamline that goes from the incoming jet to either the point 2 or 0.3 will tell you that V1 is actually equal to V2 and V3, and that the main reason is because basically the pressure is uniform along those outer streamlines because they're exposed to atmospheric pressure. So the pressure is uniform, and that means that a consequence of that is that Bernoulli says that the velocity is uniform. So when we applied conservation of mass, that implied that, well, the flow rates at each point were the same, right? So V1 turned out to be equal to V1 H1, which is the flow rate, the incoming flow rate, was equal to the total outgoing flow rate. And since all the velocities were the same, that implied that H1 equals H2 plus H3. So that was one thing that we found, but that doesn't actually tell you what the value of H2 or H3 is. So there's not enough information contained in Bernoulli's equation and mass conservation to actually solve for the geometry of the flow. So what we need to do to accomplish that is use conservation of linear momentum. So conservation of, just as a physical principle, because there's no way for shear stress to impart a transverse force onto the plate, we know that the transverse force must be 0. And what we can do then is, basically, apply conservation of linear momentum. So our statement of conservation of linear momentum is that the sum of the external forces acting on the fluid is equal to the rate of change of, momentum in a control volume, or sorry, momentum in a control volume plus the rate of flux of momentum through the control surface associated with that. Let me define my control volume here. Let me just talk about this for a second. So my control volume is going to be the same one that I had before, but just a little bit different. I'm actually going to bring my control volume down into the solid material just a little bit. And I'm going to say that, all faces of this are fixed. So if I have a fixed control volume, so the control volume doesn't move with the fluid, it's just fixed in space, then I'll just comment on a couple things here. So you'll notice here, I did not write out reduced velocity, and that's because I intended to use a fixed control volume. If I didn't do that, I would need to use the relative velocity between the fluid and the control volume. But because I have a fixed one, the control volume doesn't move. So I have a steady flow. So steady flow means that, basically the control volume is not moving. And then now, the other thing I'll point out is this is actually two equations, right? Because I'm in a two-dimensional space. Force is a two-dimensional vector, or it has two directions, two components of force. And similarly, so this term is a scalar, but this term is a vector. So this has two components. So the left-hand side has two components, and the right-hand side has two components. So this is actually two equations, not one equation. So the first thing I'm going to do is apply conservation of linear momentum in the transverse direction. So actually, let me write like a coordinate system here. So I'm going to define a coordinate system that goes, in this direction, where I'll call this the normal direction and the transverse direction. So, so let me write that equation out in the transverse direction. All right, so we've established that the sum of the external forces is 0 in that direction. In fact, actually, there's one little point here. I'm just going to write that the sum of the external forces is 0, but it's actually important to recognize that it's not just the force on the plate that contributes to the sum of external forces. There are actually pressure forces that act on each of these faces as well that contribute to the sum of the external forces. But in this case, the pressure everywhere is atmospheric pressure on all faces of our side, except for maybe here. But those forces only act in the normal direction, so I won't worry about them. But along these kind of locations, all of this is exposed to atmospheric pressure, and so the pressures everywhere are 0 if I'm working in gauge pressure, so they don't contribute. So the sum of the external forces in the transverse direction is 0 because it's a frictionless flow. And then we need to evaluate the flux term that's here. So in fact, if we assume that the velocity is uniform across here, so like the velocity at every point along these exits is just, uniform, which is what we've been doing, then we don't actually need to do an integral across the little elements of area like at these individual inlets and outlets. We can just multiply the magnitude of the velocity times the total area. So like, for example, at the inlet, So that's at this location up here. The value of this integral is just rho times v. So what is v projected onto the transverse direction? So I have to take, oops, wrong one. I have to take v1, which is the actual value of the magnitude of the velocity, but I need to project that onto the transverse direction. And so v1, so the magnitude would be v1 cosine theta, because I only want this transverse component. So it's v1 cosine theta, and then I need the value of v dot n. So what is the value of v dot n? Well, remember that it's an outward facing unit normal here, so that's the unit normal for that surface. And so the value here is minus v1. So v1 and n hat are co-aligned, but n hat is in the opposite direction. So this is a minus v1. The minus is important here. Times the area, but the area is, well, in 2 dimensions it would be basically h1 would be the height, and then you would need a depth into the page to get that 3rd dimension if you want it. But I'm gonna leave out the 3rd dimension here and treat it as a 2D flow. So treat this as a force per unit depth. So if I wasn't doing that, if this wasn't a force per unit depth, I would have to multiply by the depth into the page here. But I'm not gonna keep that term. Okay, so that's our inlet. And then we've got 2 outlets here and here. Those are easier to do because they're already projected onto the transverse direction, or at least they're co-aligned with the transverse direction. So for example, for outlet number 2, this would just be rho v2 times v2. The parentheses here is meant to represent that it goes along with that parentheses. So that's a plus v2 times the area at that outlet, which is just h2 times depth into page, plus the 3rd outlet, which is in this direction. So the absolute, remember, this is not an absolute value. This is actually includes the directionality. So in this coordinate system, the value of the velocity would be negative v3. So that's an important thing to track down. And then the value of v dot n, so again, v goes this way and the outward normal also goes in that direction. And so v dot n is v3 times a, which is just h3. All right, so if we put that all together, now remember that the velocities here are actually all equal, we found out. v1 equal v2 equal v3. So in fact, a lot of these velocities are common to each term. So I've got a v squared everywhere and a rho everywhere. And so if I cancel that all out, and in fact I'm going to move h1 to the other side too, then you can write that, so I'll cancel common rho times v squared. So what I'll find is that h1 cosine theta equals h2 minus h3. So remember that h1 was known, that's a given, and h2 and h3 are things that I was looking to solve for. And so I have 2 equations here and 2 unknowns. It's a linear set of equations, right? So I have something that looks like a constant times h2 plus a constant times h3 here, and then I have something similar here. So I can solve for those. In this case, the easiest way to do that is to just, so if I add this equation to this equation, the h3 here will cancel out, when I add the 2 equations together, and allow me to solve for h2 quite quickly. So in that case, I would get, so if I'm adding the equations, I would get h1 cosine theta plus 1 equals 2 times h2. So I'll just divide right away by the 2. And then similarly, if I subtract those two equations, so if I take this equation and I subtract this equation, that'll get rid of, let's see, the h2. So if I subtract the equations, this h2 and this h2 will cancel, but this and this will add. And so you can find that, pretty rapidly that h3 equals h1, what is that, 1 minus cosine theta divided by 2. And let's check and make sure, does this make sense, right? So does this make sense? So if theta is 0, so if theta over here is 0, then basically we're just shooting our water directly along the plate. And in that case, so if theta is 0, cosine is 1. And in that case, 1 plus 1 is 2, divided by 2 is 1. In that case, h1 is equal to h2, which makes sense, right? So if theta here is 0, basically I expect that this jet will just continue moving down the line. So h1 would be equal to h2. Let's check that in that situation, h3 would be 0, right? So 1 minus 1 is 0, and so h3 in that situation would be 0. Let's check the other extreme case, which is that theta equals 90 degrees. So if theta is 90 degrees, then the value of cosine is 0. So you would get, h2 equals h1 divided by 2. And that also makes sense. You expect that if you shoot this thing at a vertical plate, so that's what it means to have a 90-degree angle. So if the jet comes in perpendicular to the plate, I expect that this thing by symmetry should divide in 2. And so h2 would turn out to be h1 over 2, and likewise for h3. So cosine of 0 over here, or cosine of theta would be 0 in that case. So you would end up with h1 over 2 as the value of h3. So everything is totally physically consistent here. Let's check. There's one thing that we haven't done yet. So that establishes everything except for the normal component of the force. So far we have written out linear conservation, linear momentum conservation in the transverse direction. If we do that in the normal direction, we'll be able to figure out the normal force. So let me pull this picture over to the next page and do that. Nice. Hey, sit. Bad dog. All right. Where was I? All right. In the normal direction, right? So in the normal direction, if I write out the sum of the external forces, so let me write out our general like our vector equation again so that we can reinterpret it. So that was the sum of the external forces, which was a vector, equals, well, I won't write out the unsteady term this time. I'll just keep the flux term. This was the important bit. So this was the term that we really needed to figure out. So in this case, again, like the pressure along all the outside of my control volume is atmospheric. And so as long as we're considering atmospheric pressure to be 0, so we're working with gauge pressure, then that won't contribute to anything. And so we really just need to worry. So I'm going to project this onto the normal direction. So project, or I'll just write out the normal component. So in that case, our external force is just the normal force acting on the bottom of the plate, is equal to the sum of the fluxes coming into our various surfaces. So we've got fluxes here, here, and here. Now, one thing that's kind of nice here is that if I look at, I guess it's this, right? So if I look at this, the normal component is actually 0 here and here. Like basically this velocity is only in the transverse direction. So those two ports actually don't contribute at all to this term. So, and that's just because, again, the velocity vector is just aligned there with the transverse direction. So there is no transverse component. So I really just need to project the entrance here onto the normal coordinate. So let's do that. So that means that this would be rho times v projected onto the normal coordinate. So v actually goes this way, and I need to project that onto the normal coordinate. So that would be minus v1, and then I need to project it onto the normal coordinate here, which is just the sine of v1. And then I need to take care of, so that's this term. Now I need to take care of v dot n. So what is v dot n on that surface? So again, v goes this way, but n hat goes this way. So this is a minus v1 times a. And so the two minus signs here cancel, and you can put it all together and find that the normal component of force is just rho v1 squared times a sine theta. And does that make sense, right? So if, let's see, so if theta is 0, right? So if theta here is 0, I wouldn't expect there to be a normal force, and let's check it out. So if sine of 0, yeah, that turns out to be 0, so there would be no normal force. And similarly, if theta was 90 degrees, I expect the value to just be this. And that works out because sine of 90 degrees is just 1. And so everything here works out, and so we're able to solve for both the normal force and the two component, and the two thicknesses of the layers that split, as well as using Bernoulli's to figure out the velocities. So a key insight here that makes this possible to solve is that we're going to approximate the flow as frictionless. If we did not do that, there would be things would be a little bit more complicated, because we'd have to consider carefully what these velocity profiles look like at the exit and relate them to shear stress. And I think actually that would be difficult to do without some approximation of what the velocity profiles look like. But anyway, so for a frictionless flow, though, it's actually quite easy to write out these kind of momentum balances. All right, so that completes that problem. All right, here's the Python notebook where I actually kept track of what these numbers were. So I'll just write out the numbers. So these were the numbers that I was using to solve the problem. So I had an inlet pressure of 200 kilopascals, an initial diameter of 100 millimeters, and an outlet diameter of 25 millimeters, and the density of water was 1,000 kilograms per meter cubed. So you can calculate the areas right away as pi, r squared. So for A1 and A2, and the area ratio turns out to, I believe, be, what is that? I actually don't know what that is as a number, but it's pretty close to, I think it's 1 out of 16. In any case, so at one point we found using Bernoulli's equation that V2 was given by the square root of P1 divided by half rho 1 minus the ratio of areas squared. And so I can evaluate that now that everything is sort of plugged in here. And you find that the outlet velocity is 20 meters a second, and the inlet velocity was 1.25 meters a second. The more interesting thing is probably this reaction force. So we found that the reaction force was minus P1A1 plus m dot V2 minus V1. So now that the velocities are known up here, I can actually evaluate for m dot. So m dot is just rho VA. I could either do this at V2 and A2 or V1 and A1. So I just did it here for V1 and A1. So m dot turns out, who cares what m dot is? So you can separately calculate the pressure term and the momentum gain term. So that's what I'll put out down here. it turns out in this case that the pressure term is actually quite a bit larger than the momentum gain turn. So like by, about a factor of, I don't know, 10 or so. So the pressure, really, it's mostly the pressure difference that's causing the reaction force on the solid part of the nozzle. And so it turns out that, to maintain the nozzle in place, you actually have to provide a leftward reaction force of, 1,300 and some change newtons in this case, which means that like if I wanted to attach this nozzle to a hose, I would actually have to have some bolts that would be in tension, acting on that nozzle. So recognizing that a negative reaction force corresponds to a leftward force is sort of an important insight into this problem. But in any case, so those are the numbers that come out after you evaluate them.